Hello, so here's a tutorial on how to get a wet map or a persistent selection transferred into vertex color in Max using MCG. We've got this basic simulation here that was done in Mass Effects. I'm sure you can figure out how to do something like this. So we'll take a look at how this works real quick. So here we've got a soft selection as the ball rolls down here. So then from this soft selection, we have a soft selection to pick RGB. So I've hardwired some RGB colors in there that it is just changing soft selection into RGB. For this tutorial, we're going to walk through the MCG graph editor, and I'm going to try to describe what I think is going on. I am by no means an expert at this, and I didn't write these flows. These are both pieces that I received, but in an effort to try to figure out what's going on, I went through, took some notes, and I'll walk you through this. If I'm saying something wrong, if you wouldn't mind putting it in the comments or shoot me an email or something, and I will get in there and fix it. But like I said, this is to the best of my understanding what's happening here. So the first thing we're doing in MCG is we've got this node picker. I've picked that yellow ball here. Right after that is a node that is check node validity. That just says, hey, don't run this flow unless you actually got something picked there. So those are pretty straightforward. Where we go from there is into this group of nodes, which computes the fall off distance between each vertice and that node that we picked. So this compound here is kind of, this is one that ships with Max, and it's doing a lot of the heavy lifting. It's got 3 ports to bring data in. It's got the node, which is the pick node we're picking over here, and then it's got this point, which is the vector 3 position of a vertex. And then it also has a matrix, and this matrix is the position that if you multiply using modifier matrix by this position, it takes this node that you've picked, that ball, and puts it into world space. So this compound here, mesh vertex to node distance, is sending out a float single, which represents the distance between a vertex and the node. Node number 3, effect region, takes that distance value and some parameters from the UI you see down here, fall off bubble pinch, and it makes a region similar to what you've seen in subobject soft selection. You'll see that we've left one of these ports open. Because we're dumping out this effect region as a function, this becomes our independent variable for this next map node that's over here. So one way to think about it is this vector 3 is receiving vector 3 positions from this node 11 mesh vertices, and it is using them as we map this effect region onto each one of these vertices. Our second little grouping here is for each vert get fall off value. Node 11 here is called mesh vertices. It's taking the modifier's mesh and it's outputting an array of vector 3 positions for each vert in the mesh. So then it dumps out that array into map here, and this map takes this array and transforms it by this function coming in. The function puts a single fall off value for every vertice into each array element. This in itself could be an MCG modifier that really is just a soft selection by node if we were to pipe it out here. But we're going to take it further. Martin has built up this whole section in the middle here, which is going to keep a history of the soft selection in a cache, and then it also is going to say, hey, whatever the highest value is, that's what we're going to keep. And that's really kind of the meat of how this persistence works. So first thing we do, we have that array that we kicked out from every vertice now has a fall off value. It has a float single for every vert, how selected it is. And that really kind of acts as in any particular frame. So we would update every frame, or maybe in our case twice a frame, and that soft selection would move around. What we want to do is cache it, which is to say take a picture of this array at every timestamp and keep those in memory. So that's what this create cache is doing. I don't fully understand what's going here, but what I'm thinking is number 20, node 20 here, create cache, it needs 2 functions, one to initiate the cache and another to update it. The depth here, this third one, tells the cache how many frames worth of data to hold. So this is wired into our parameter persistence, and you saw that out in the UI. So this is how many frames of this array do we want to hold. So it appears this create cache node is storing a bunch of arrays of singles to the depth passed in. The default is 10. That means 10 arrays one for the soft selection at each frame of this whatever persistent value in here. So it would be 10 frames worth of soft selection arrays. The whole piece of geometry, all the different soft selections stored 10 times. So essentially we have an array of arrays. Going down here to the set depth duration. So we talked a little bit about the persistence here. We're piping that into the depth. That's how many of these arrays do we want to store here. So this range says it makes an ordered array of integers from 0 to n1. So it's making, in this case, it's making an array with 10 slots in it. This section down here returns an array of zeros if the cache entry is not available yet. So before the cache starts, it's going to throw all zeros, and when there's a 0 passed into soft selection, that's basically deselected, and a 1 would be fully selected, and somewhere in between would be somewhere in between. So I'm not sure about how cached value at depth 0, what exactly it's doing. I think it's just to get the amount of items in the initial array with no cached information in there. The second note here, we make an array of zeros. So we take that cached value, which is the number of items in the array, and we do a count, and we make an array of zeros. So however many items are in that array, we're going to make a bunch of zeros here. And now we've got this if test here. Bring it up to here. We have another node called pass cache data if available, and it's saying, hey, if there is a cached value, we are going to say true and send that cached value through onto the flow. If that cache value is a false, is there anything in the cache? Then we're going to send this array of zeros. We then map that cached data by how many depth steps we have set here. So this is really where we're making our array of arrays. This node takes this range from node 19 range and transforms it with the cached array, or the array of zeros if there hasn't been anything cached yet, essentially making an array of arrays. The array of array goes into a custom compound that Martin Bright wrote here, MB max of arrays, and let's pop open that to see what is going on inside there. We got an array of arrays coming through. This pass-through is going to pass it to these two sections. We'll go up here to the first one. So this flatten node here concatenates the array. So we have multiple arrays within an array. This takes those and flattens them. I'm not sure on this, but I'm thinking it's either making a very long array or a very tall array, but it's really packing them all into one array. And then we have this below here, number of elements. It looks at how many arrays are in the first array and assumes each array is the same size and sends out a count of how many arrays exist. I think there is one for every level of depth set earlier. So if we have a level of 10, our default, I think this is sending out, there should be 10 arrays in there once that array has been filled with 10 frames worth of data. So in this group over here, Martin's calling a reshuffle, we create an array of arrays with corresponding elements in each array. It seems to take this flattened array, concatenated array, into a stride node, which skips every n elements. In our case, n is the value put out by that 15 count down here. Or another way to think of it is it's the depth of our cache, and also the number of arrays packed into this input array. So this open port from int32 here, I think this serves to send out corresponding elements from different depths, or times is another way to think of it about it. We can compare these soft selected values at different times and then map them by the functional maximum element. So what this setup is doing is comparing soft selected values at different times, and then we map by the function maximum element, creating a new array which successively builds up to whatever the max of that element has been. And then from there, we're dumping back out into the compound. We'll take us back out to node persist here, out of this max array, and then that final array of information is set into the soft selection. So if we go back to our max file, we can see that as our node comes within the fall off proximity here that we've set, and we'll raise that up just to see what that looks like, of these verts, effect region makes this region, that gets pumped into a cache, which is then holding the highest value for n number of frames here. And that is the basics of this. So in part 2, I'll go through how we take what is a soft selection and we convert that to an RGB color value, and we pipe that into Vertex Colors. Stay tuned.